Chapter 9 More circle. Let's review a more example in more circle and stress transformation. So in this example, the state of plane stress at the point is shown on the element below. We want to determine the maximum shear stress at this point. So an element is given by a 20 megapascal push at X and a 60 shear in X and also a 19 pull normal stress and also a 60 again shear stress. Let's develop the Mohr circle. So if we develop the Mohr circle for our sample, so it just goes by a negative 20 and 60 megapascal tends to rotate the X element counterclockwise. So that's a point which goes below X axis. So that's a negative 20, a push of 20, a compressive force of 20 megapascal, and a negative 60. Just modify this one. That's a negative 60, which is a counterclockwise, which brings the point below the x-axis. So it goes by x, which a negative 20, which is a 20 megapascal push, and negative 60, which is a 60 megapascal and counterclockwise rotation, and bring us to a y of 19 tensile stress, which goes by y in positive 90. And if you look at the y element, it just shear tends to rotate it clockwise, so that comes to the above of x-axis, and that's a positive 60. So our data is sigma x a negative 20, sigma y a positive 90 megapascal, and tau xy 60 megapascal. And we just have created the Mohr circle based off those 2 points. And again, sigma average is sigma x plus sigma y over 2, and that's a negative 20 plus 90 over 2 gives us 35, and that's 35. Sigma average is from the origin to the center of our Mohr circle. And at the same time, r is a square root of 60 squared plus 55 squared. And 55 is just c to f. Mhm. If we call that point f, mhm, so this is f, and cf is just simply sigma x this time minus sigma y over 2. And if you do the math, it gives you sigma is a negative 20. Mhm, mhm, minus a 90 over 2. So that gives you a positive. So let's put it this way, sigma y minus sigma x. Mhm. So the higher sigma y is 90 minus sigma x minus 20 over 2, because we need to go with the higher, and that gives you a 55, and that's 55. Mhm. Let's make it a bit clean, and that's the first step in calculation of r. And then r, which is this part, it just simply cf squared plus fy squared. So that's a tau, which is 60 squared, and cf is 55 squared, and it gives you 81.4 megapascal. So tau max is equal to R, and that's 81.4 megapascal. So again, sigma average is 35, and R is tau max is equal to 81.4 megapascal. Mhm. And if you just want to calculate sigma max and sigma min, it just gives you a sigma average plus R, sigma average minus R, 35 plus 81.4, and 35 and minus 81.4 gives you a sigma mean of negative 46.4 and sigma max of 116.4 megapascal. And again, tangent of 2 theta p, if you call that 2 theta principal by a rotation from the origin, it gets you to sigma max, and tangent of 2 theta. Let's calculate tangent of 2 theta p and what the theta p is. So if you look at the Mohr circle tangent of 2 theta p, mhm, which is here, it just simply tangent of this is just simply rise over run. So that's a 60 over 55, and 2 theta p is equal to 47.49. And again, theta s is just a 90 minus that angle. So if this is 2 theta p, and if you just subtract, let's go by a, so this is maximum tau, and that's just a 90 minus theta 2 theta p. If you do the math, that's 2 theta s. That's 2 theta s. If you just go from the origin by 90 minus 2 theta p, it just gives you 2 theta s. This is 2 theta p. 90 minus that degree gives you 2 tau maximum, and that's 2 theta s. If you do the math, 90 minus 2 theta p, it just gives you 42.4. And that's a theta s is just divide that by 2. That gives you a 21.3. Yes, so that's a 2 theta s, and just theta s is a half of that amount. So that's theta s. It just brings you to x prime, which is the plane of tau maximum equal to 84. And if you look at the normal stress of tau maximum plane, that's simply 35, which is sigma average. Let's review another example. So the state of plane stress at a point is shown at the element below. Determine the stresses on the element on an element oriented 30 degrees counterclockwise from what you have. So in example 3, it just simply says if we uh, rotate our element in a counterclockwise position with 30 degrees, now calculate the stresses. So that's a normal and a shear stress. So we do know a 30 degrees in plane, it's a 60 degrees, twice of that in Mohr circle. Let's solve our problem. So it simply says if we want to draw the Mohr circle, it just gives us an x by a negative 8, which is a compressive stress, and a 6. So the shear or friction or shear tends to rotate our element in a clockwise direction. So that's a point above the x-axis. And the other one is a 12 KSI, so a positive 12 normal stress. And if you look at the same uh, shear stress, this time tries to rotate the element in counterclockwise. So that's a point in below x-axis, and that's a negative 6 for y. Mhm. And if we just want to know what the stresses on a degree after a 60 degrees counterclockwise. So a 30 degree in counterclockwise in element again is a 60 degrees in counterclockwise in Mohr circles. So in that sense, we want to know what are the uh, stresses in this plane. Mhm. After a 60 degrees counterclockwise rotation in Mohr circle. So let's see how that goes. So sigma average is simply sigma x plus sigma y over 2. That's a negative 8 plus 12 over 2. That's 2 KSI. And r is radius is the square root of 6 square plus 10 square. And that's a simply comes from here. So r is center, and if we call that f, that's tau squared plus cf squared. So that's cf squared. And cf is simply sigma x minus sigma y over 2. Sigma x is a negative 8, sigma y is a negative uh, positive 12 minus 12 over 2, and that gives you again go with the higher one. So that's a 12 minus a negative 8 over 2. That's just simply due to the direction. So you can go either way, but careful about which one is the bigger. So that's a numeric value of CF is equal to 10. That's a negative 10, but we just need the square root of that. So it just gives us a radius of 11.66. So radius or tau maximum is 11.66. And in from from plane A, normal x0, point A, which is a negative 8 and positive 6, stress on 30 degrees element from a counterclockwise rotation create line CP, get us to line CP. Hmm? So that's the line CP. And if we want to know what are the stresses on CP, we need to just go by a geometry. Let's make it a bit clean. So the total angle is 60 degrees, twice of 30 degree in Mohr circle. And let's first calculate a theta, which is a tangent, arctangent of 6 over 10. So that's 6 over 10 rise over run. Mhm. And that gives you a phi equal to 30.96. And if you want to know what is the rest, so if this is 60, the other one is just 60 minus that angle. So that's a 60 degrees minus 30.96, which is phi, and that's 29.04, which is this angle. Why we need that? That's the projection of R in X and Y gives us the shear and normal stresses on the new plane. So let's see how that goes. A plane of CP. So if you look at the this Mohr circle, sigma x prime is just simply sigma x prime. It's simply the translation of R. This is R, and that's equal to 11.66, and this angle is 29.4. So R cosine of theta, or if something like cosine of uh, beta, for example, and this is beta, it's a just sigma x prime, which is their x normal stress of x prime, if we call that x prime, and that's 2 minus sigma average minus that one. So sigma average, which is C from our center. So let's highlight it here. If you subtract sigma average, which is origin to C, that's a 2 minus 11.66 cosine of 29 gives you a negative 8.2 ksi, and tau x prime y prime is simply the vertical component of R. So that's a 11.66 sine of beta. It gives you a numeric value of tau x prime y prime, and that's 5.66. And that's the answer for stresses on a plane by a rotation of 30 in the element. Thank you.